Good afternoon. I'm Jay Scott, editor of ASHRAE Journal. Thank you for joining us for today's webinar, part of the ASHRAE Journal Supplier Webinar Series, providing information to journal readers and others about products and technology for industry professionals. ASHRAE does not review supplier webinar presentations. Cambridge Engineering welcomes you to today's presentation, Cooling Industrial Facilities, the Evaporative Advantage. Today's presenter is Dave Binz. Dave is the Director of Engineering for Cambridge Engineering. He holds a Bachelor of Science in Chemical Engineering from the University of Notre Dame and an MBA from Washington University. He has extensive experience in the high-efficiency heating, ventilation, and air conditioning market. He began his career with Carrier Corporation, serving the large commercial and industrial market with engineered solutions. He joined Cambridge as a regional sales manager and now travels North America speaking to engineers, building owners, and contractors on next-generation heating, ventilation, and evaporative cooling solutions. Dave is a member of ASHRAE TC 9.2 Industrial Air Conditioning and Ventilation Technical Committee. Today's moderator is Randy Niederer. Randy is the Director of Marketing for Cambridge Engineering. And now we turn the presentation over to Dave. Thank you.
Hey, and welcome everyone all for spending me today and talk a little bit about some trends here in industrial manufacturing facility spaces. What are we seeing? What are some of these clients seeing? How is it changing? And in addition to that is how can this evaporative cooling technologies be helpful in this changing market for these clients? So a background for Cambridge Engineering, for those that aren't familiar, we are a manufacturer based in St. Louis, Missouri, and we have a over 50-year experience of helping clients in a variety of large commercial and industrial spaces. Over 50 years, we've helped over 5,000 contractors provide 30,000 plus installations and have gone back and actually documented the savings and performance of these technologies. And we're really excited about this change in the industrial market and how these technologies can help us. We have people have probably know Cambridge very well for some of our other industrial space heating and ventilation technologies. And with the addition of a recent acquisition of evaporative cooling technologies through SpecAir, we have a variety of evaporative cooling technologies that can serve these large commercial and industrial spaces. One of the things that we try to do here at Cambridge, and one of the things that we see in this industrial space, is that we are trying to help leaders create a better working environment for hardworking people. If you think about the industrial space and warehouse manufacturing, typically it is seen as a dark and dirty environment. If you think about the employees and how we look at the employees in the industrial spaces versus maybe the employees that we see in the typical commercial space, and there has been this difference of standards from how the indoor comfort and safety and thermal comfort has been applied. One of the things that we have seen is that that is changing as we are seeing very low, historical low unemployment rates. Employee retention is getting harder. Not only that, there has been an increased awareness around thermal comfort and safety and ventilation to actual worker productivity in addition to retention. And one thing that we are trying to do is we're actually trying to help business leaders solve this problem. This has been a problem for industrial facilities for ages. And the thing that they've seen historically is when they look at the economics of trying to deploy cooling technology into some of these spaces, is that there is a big disconnect with how much I can afford, what are the benefits of the technologies, how much is it going to cost me to install, and the things that I'm trying to provide. However, as the market has changed, customer requirements, technologies have changed, we believe we are on the cusp of this changing trend to industrial spaces where more facility leaders are looking at a bigger picture, more than just the upfront and operating costs, and looking at all these other business costs, as well as what new technologies can do to make these applications more of a viable option in these industrial facilities. So like we said, what are some of the trends we're seeing? Major investments are being made today. We are seeing large warehouse spaces, which in the most common sense have been primarily ventilated and heated spaces only. That is shifting. These large warehouses are now looking at providing some level of cooling or comfort where they may not have done that in the past. Some of that is being driven by productivity, but a big driver has been, like we said, that recruitment and retention has become much of a more driver in this industry. And what has also been interesting is that as the major players in this space have made this shift for the variety of reasons that we spoke before, is that now that is influencing and making competition for employees even harder. Those seeing that now as large players shift towards having these spaces air-conditioned or providing better thermal comfort, it becomes even harder to attract and retain those employees. So what has started in a few key areas with some of the early adopters is now creating this windfall throughout the industrial facilities. So if we look at what options are available to these industrial facilities today, the customers have a variety of options available to them. And as we grow in complexity and installation costs, we are able to provide more comfort, but depending on the economics of the project, the customer, and the complexity of the application itself, some of these technologies may have been cost prohibitive in the past. If we think about just the general entry level to providing thermal comfort in the summertime peak conditions, really the first step is general ventilation exhaust. If you would walk into a typical large warehouse distribution or an industrial facility, the first stage they're going to do to provide relief from the heat stress and solar and skin loads of a building is try to provide a very high level of air changes to relieve that heat stress, create more air movement, and get a more comfortable working space. This has very low cost, low complexity, and low operating cost to enter into some level of space conditioning. If we think about the next step, the new entrant into this space in the last 20 years has been the innovation in the HVLS fan market. These very large fans have been able to provide a massive amount of air movement to provide more comfortable working spaces at a lower cost and really an increased comfort level than traditional air movement technologies. And really, if we think about those two technologies have been the most widely spread adopted cooling technologies in the large industrial spaces. And for years, more often customers make the jump from the fan and general ventilation fans up into mechanical cooling systems. And if we think about that, that is a very big jump that most industrial facility leaders have had a difficulty swallowing or justifying in their spaces. And what we're going to talk about today is get a little bit deeper into what are the options available from cooling or tempered ventilation or the evaporative technologies that we see being deployed in these spaces. So again, if we think about our clients are trying to climb the ladder, so to speak, as far as what levels of comfort or complexity they can justify in order to provide that greater level of thermal comfort to the space. And really what we're going to try to nail down today is how exactly are these new evaporative technologies, the ones that are probably very familiar to you all, and also maybe some of the newer evaporative cooling technologies that may have been deployed in specific markets, specific regions, or specific applications. And we're going to talk about what are the pros and cons and how can we actually see more adoption of these technologies to help bridge the gap from a general ventilation HVLS fan type of system, which is never going to be able to exceed the types of thermal comfort without more temperature depression, but not get into the high levels of complexity, installation costs, or operating costs of traditional mechanical cooling systems. So let's talk about some of the trends inside of the evaporative cooling technologies. We're specifically going to be looking today at large industrial facilities. Sometimes this may be large warehouse, distribution facilities, large manufacturing facilities, or even full heavy industrial applications. These buildings are typically large, have high ventilation requirements because of whatever type of operations or processes they have inside the space. They are typically high bay with very large ceiling to height ratios, and also typically have a very high sensible heat ratio compared to your typical office space or other commercial space. So today, I want to talk and drill deep into what are the actual psychometrics and the actual thermodynamics of the three major types of industrial evaporative cooling. Most people are probably familiar with the direct evaporative cooling. It is widely adopted and spread through most of the Western climates. We'll talk a little about why. But it is still also deployed in other markets outside of Western dry climates for specific applications and building conditions. We're also going to talk about the indirect evaporative cooling technology, how that differs from direct, what is the actual process difference, the type of technology difference, and how might that change my ability to apply it based on job site conditions or project application. And then we're going to go into two-stage, which is your indirect direct, where we actually combine the benefits of both technologies and can get even more capacity or temperature distribution, and how that process looks like on a psychometric chart, and then how we might be able to deploy this in these industrial facilities where they have not been deployed before. And hopefully get our industrial clients who are, again, trying to solve this age-old problem of making a safe working environment, making thermal comfort more attainable and attractive to their organizations. So first, we're going to go with the lowest complexity and lowest entrance into the evaporative cooling technology, and that's the direct evaporative cooling. So direct evaporative cooling, more probably commonly used as the swamp cooling technology, if you will, but really I think that brings a negative connotation to it. But what direct evaporative cooling is it is a direct adiabatic constant enthalpy cooling process. What we do is we are taking the warm, hot air, drawing it across a wetted media, and as that hot air transfers the energy to the water on the evaporative media, we are evaporating that water, transferring that energy, which is allowing us to depress the dry bulb temperature. But then as we are evaporating that water and we are adding humidity to that airstream and actually having a humidification effect. So that's where the cooling through a change of state happens. One thing I think that has become a more common conversation in these industrial facilities as we are seeing the rapid transition of our vapor compression systems, and as we are seeing refrigerants change, also previously the last 15 years, but also the changes that are going to be happening in the next 5 to 10 years, in some cases have already happened, is the beauty of the direct evaporative cooling is that we are using a natural refrigerant, if you will. We are using water, so there are no CFCs, HFCs, or any other type of refrigerant that would add to global warming potential. And the major, I would say, benefit of direct evaporator is that it has been shown in a lot of the hot, dry climates that we can provide a high level of cooling at a much lower energy usage compared to vapor compression technologies. So what does this technology look like? So what this looks like is, as we mentioned a little bit previously, is you have a wetted media that is a plumbing system and a pump that is continuously recirculating water from a sump to the top of the media, and we are trying to get a media fully saturated such that when the hot air comes across, we are trying to evaporate as much of the water as possible and get to some level of dew point in that air. We are trying to keep that media at a less than 500 feet per minute to avoid any sort of water carryover, and these media has a very, very low pressure drop compared to other common heat transfer devices such as a DX coil or HO water coil. So very effective at transferring energy and very low energy required for your fan and your ducted systems. The media itself, for those that aren't familiar with this media, there are various types and constructions of the media. Most commonly used in some cellulose form or other fiberglass media is available to meet specific requirements. But what we're seeing is you see the water droplets that are being dispersed across the top of the media, and as that saturated media is introduced to the hot, dry air, a collection of that water is going to drain all the way through the media and then get recirculated, but a large portion of that is going to actually be evaporated and provide that cooling effect. So there are various types of sizes, technologies, or construction of that media. And the type of efficiency, and really when we're talking about efficiency in direct evaporative, we're talking about effectiveness. And the effectiveness is how much of the difference between dry bulb and wet bulb am I able to transfer during the evaporative cooling process. So if, for instance, we have a 30-degree depression from dry bulb to wet bulb, a 90% evaporative effectiveness will essentially bridge the gap 90% of the way between my 30-degree temperature depression. So 90% times 30 gives you a 27-degree temperature depression. And depending on the face velocity coming across that media, as well as depending on the thickness of that media, you will have different pressure drops and different effectiveness. And I think when we look at the application, one of the things we need to take into account, based on your job site conditions, what type of cooling you're trying to provide, what kind of internal loads we have, we would look at a varying type of construction, thickness, and face velocity in order to provide the maximum amount of cooling effect to these facilities. So let's look at what that's going to be on the psychometric chart itself. So if you recall in the previous slide, we talked about direct evaporative is a adiabatic cooling process. It follows a constant enthalpy line. So we're going to look at this from two different climate zones. First climate zone we'll look at is climate zone 2B, which would be your more traditional direct evaporative market. It's the hot, dry area in the Southwest. In this case, this will be looking at a Phoenix, Arizona type of an application. So if we look at this and we're looking at our psychometric chart, we have our entering air, our ambient air coming in at 110.2 dry bulb and 70-degree wet bulb. The degree depression between dry bulb and wet bulb is about 40.2 degrees. We look at a typical direct evaporative and effectiveness, and what I'm able to achieve through direct evaporatively alone is a leaving air temperature of 74.3 degrees dry bulb. So we had almost a 36-degree temperature depression. If you looked at the wet bulb itself, my wet bulb did not change, right? And that's what we anticipated. Because this is a constant adiabatic system, it is a constant wet bulb process. So your wet bulb will not change. If we try to think about that in this more traditional calculation, that's about 32 tons of sensible cooling capacity on a 10,000 CFM basis. Now, of course, our working element, if you will, is going to be the water. That's going to be the energy, so to speak, that we're using to provide this cooling effect. In a 10,000 CFM, that is only about 0.6 GPM of evaporation. So while there is some evaporation and using of water conditions is a very low amount comparatively than some of the other pumping systems that we are probably more fondly familiar with. So now let's think about we're outside the arid climates of the Southwest, and we're looking at a more traditional, what I would say, industrial facility in the Midwest. And let's move to climate zone 5A. Let's take, for instance, this may be an application in, say, Chicago, Illinois, large industrial space. Obviously, my entering conditions are going to change dramatically. We are not as high of a dry bulb temperature, and we have a little bit of a higher wet bulb based on the humidity of that geography. In this case, we have a dry bulb of 89 degrees and a wet bulb of 73.4. This gives me a 15.6 degree depression between dry bulb and wet bulb, and having the same effectiveness in the same application as we had before, we get a much lower temperature degree drop, only about a 13.9 degree, but still my leaving air temperature is now 75.1 dry bulb and 73.4 wet bulb. Now you may say that's not as good as we had in the Southwest region. However, that's a fairly sizable amount of cooling and a much lower temperature than direct ambient. And if we think about, based on a 10,000 CFM application, that may be roughly 13 tons and a very low amount of water evaporation. Now, let's try to step out of our common applications of the commercial office spaces or other type of commercial buildings, and let's think about some of these industrial facilities. You know, some of these spaces that we're looking to apply have extreme temperatures. We may be looking at anywhere from applications from 90, 95, 100 plus. We've even seen some where it's 110 degrees inside of a industrial facility because of some level of process heat or other type of process application going on in this building. And we may actually see that at a higher temperature in this space, and depending on what kind of application in the space, we actually may be able to get a pretty demonstrative cooling effect, and whatever amount of added moisture may be acceptable as we look at the psychometric chart of the entire process, depending on what the current working conditions in the space. So one thing to remember is, and think about direct evaporative, widespread in the Southwest climate for a variety of industrial facilities, warehouse, distribution, and heavy industrial. And even as we get outside of the typical dry, hot applications in the Western climates, is that we actually still see some applications in industrial facilities where this type of technology may help bridge the gaps, again, to provide a more safe working environment for facilities that maybe don't have as much temperature control in the space today. So now let's look at the indirect evaporative cooling technology. This is a really newer technology, particularly in the industrial spaces. And what the indirect evaporative cooling technology does is now, instead of it being a constant enthalpy process, we are now a constant dew point process. So it is a sensible only cooling device. What that means is that now I am not adding any humidity to the airstream. So if I did have an application that could not allow any added moisture to the air because of either the geography or the process itself, I now can still get a net cooling effect with evaporative technologies and not add any moisture to my airstream. How does it do that? What it does is it utilizes a plate frame heat exchanger to separate my ventilation or supply airstream from my working airstream, or the scavenger airstream, if you will. And what this does is that now all of my evaporation process, my wet side of the process, is going to be completely separated from my ventilation process. So whatever, as the water evaporates and as that transfer of energy goes through that plate frame heat exchanger, I am transferring only sensible energy from the wet side to my dry side or my ventilation side. Now, most applications, they're going to be using ambient air as your scavenger airstream. However, there are many applications that are actually using building air as my scavenger airstream. So I can get the benefits of indirect evaporative cooling as well as energy recovery during winter or summer months to help even further the temperature depression of my ventilation coming into the building. So what does that look like? As we mentioned, it looks a lot like a plate frame energy recovery device, if you've seen one. However, there's a few key differences. What the indirect evaporative heat exchanger is made of a polymer plastic material, and the plates are a little bit wider spread than maybe your more traditional plate frame energy recovery device. However, they operate very similarly. But if you look at the picture in the top left, we have our ambient air coming across the ventilation side, and as a plate frame heat exchanger, we are alternating plates such that there is no cross-contamination, and we have the ventilation air going through the dry side, and we have in the representation in the top left, we have our ambient air, our scavenger air, or our wet air. And what we are doing is we are continually recycling water from the sump to the top of the wet media. We are trying to saturate and completely coat the wet side of the heat exchanger media on that scavenger airflow, and whatever water vapor gets evaporated, as it transfers that energy from the hot air stream coming in the ventilation, that water vapor then is exhausted out the top of the scavenger air through the scavenger fans, so you have that hot, moist air coming out of the working side and into ambient. This has a little bit of a higher pressure drop than the direct evaporative media because it is a little bit thicker and a little bit deeper. And also we're going to have slightly lower efficiencies or effectiveness, if you will, than the direct evaporative because we are not taking the air in direct contact with the water molecules themselves. So we're going to see efficiencies or effectivenesses in the 60 to 80% range, depending on your application and really depending on your phase velocities. Like the direct evaporative media, you have different types of effectivenesses based on your velocities and thickness of the media. With the indirect evaporative technology, you're going to have a varying effectiveness based on the ratio between vaporizer air to primary air. Essentially, you think about it as if I have 1,000 CFM coming in my ventilation air, if I have 1,000 CFM going out my scavenger air, I will get more effective transfer than if I only had 500 CFM of air going through my vaporizer fan. However, we want to try to keep those somewhat equal pressurized, so depending on the ratio of vaporizer to primary airflow, you'll have a varying available phase velocities across the indirect media. So a lot of it will depend on what your application is, what are you trying to accomplish, what size of equipment will we need, and then how am I getting my vaporizer air, whether it's from the building or outside, to, again, reach the optimal performance of that technology for the application. So let's look at the psychometrics of this. We're going to, again, as we did before, look at the two different climate zones and look at climate zone 2B versus 5A. So if we take climate zone 2B, again, we're back in an industrial facility in Phoenix, Arizona. We have the same entering air conditions, 110.2 and 70-degree wet bulb, the same depression. However, now my effectiveness drops a little bit because, as we said before, we now have a heat exchanger and some inefficiencies of the heat exchanger versus the direct evaporative process. However, I'm still getting 30.8 degree temperature depression. And now if we look at what the resultant leaving air temperature is, we are able to achieve a 79.4 dry bulb and a 61.1 wet bulb. So now we actually saw both the dry bulb and our wet bulb temperatures depress. If you look at the dew point, however, our dew point would have remained constant because this is a sensible-only cooling process. If we try to correlate that into some level of tempering calculations, that would be about 28 tons based on 10,000 CFM, and again, very low amounts of water evaporation, but there is some water evaporation because the water is essentially our working fluid in this process. Now let's move over to our 5A climate zone, or Chicago, Illinois. 89-degree dry bulb, 73.4 wet bulb, the same degree depression. Now again, we are looking at a 76% effectiveness, which is less than my direct evaporative, but still I can get about a 12-degree depression inside of that zone and a resultant leaving air temperature of 77.1 and 70 degrees. Now if we think about that, obviously it's not as low as some of our more common traditional vapor compression technologies. However, if I'm an industrial leader or industrial facilities leader and I'm trying to provide cooling to my space, and really the only way I was able to provide any relief was trying to provide 2, 3, 5 air changes of 89 degrees, that additional 12 degrees of depression may actually get that space much more comfortable, much more of a safe working environment, and provide more of a cooling effect than the general ventilation would have. Combine this technology with the additional high velocity, low speed fan, and I can get a very effective and a very comfortable space comparatively what they were before. If we look at the cooling effect, that is about 11 tons based on 10,000 CFM and a very low GPM. So now we're going to look at the third type of evaporative cooling technology, which is two-stage. And really what two-stage does is it combines the benefits of both direct and indirect in tandem by taking the two and putting them in series. We have the first stage is going to be your indirect evaporative cooling, my sensible only device, which lowers the dry bulb and the wet bulb. And I'm going to be mounting a direct evaporative cooling technology on the leaving side of my indirect evaporative to get that extra temperature depression that I need if I need a little bit lower leaving air temperature to provide the type of comfort that I'm trying to achieve for our clients. So how does that look on our psychometric chart? It is a two-stage process. Our first stage being that strictly sensible process that's going to follow my dew point line. And then as I depress my dry bulb and wet bulb, I now have a new wet bulb to be operating and calculating my temperature depression across the direct evaporative media. So let's actually go through the numbers. Let's again go back to climate zone 2B, our hot, dry climate in Phoenix, Arizona. My entering air conditions are still 110.2 dry bulb and 70-degree wet bulb. And if we see the first stage is going to take us down to that same point that we calculated in our previous example. We're getting to 79.4 and 61.1 degrees Fahrenheit wet bulb. Now that 79-degree air is then entering my direct evaporative media. My temperature depression now here is different. I'm looking at 79 minus 61, so I have around an 18-degree depression. Again, now that we're using our direct evaporative media, I have a much higher effectiveness. And if I take my roughly 89% effective with the 18-degree depression, and now I'm getting over a 16-degree additional temperature depression through the second stage, such that as a system altogether, I'm able to achieve a 63.2 degree dry bulb leaving air temperature and a 61.1 wet bulb temperature without any vapor compression technology. So I went from 110 degrees all the way down to 63 degrees by using only evaporative cooling technologies, by only using water as my energy source. This calculates out to be over 40 tons of effective temperature distribution or tempered ventilation based on a 10,000 CFM application. How about my climate zone 5A? Let's go back to the industrial facility in Chicago that is dealing with very high temperatures, very high ventilation loads, and it's trying to provide some more level of cooling effect in this space. And let's go through the numbers. We still have our same conditions as before, 89-degree dry bulb and 73.4 degree wet bulb. We take the same calculations and the same leaving air temperatures of our indirect process as calculated before. We are leaving that indirect media at 77.1 dry bulb and 70-degree wet bulb. and now I have different numbers and a different performance of direct evaporative media. I now have a 7.1 degree depression from dry bulb and wet bulb. Using my 89% effectiveness, I'm getting roughly another 6 degree of temperature depression through my direct evaporative, or the second stage of a two-stage evaporative technology. So if we look at it again, if I'm in a large industrial facility, I'm able to provide roughly 71 degree air into a very hot climate that can provide a considerable measure of temperature comfort that was not being achieved if I was using standard general ventilation fans. So where does evaporative cooling make sense? We just looked at 2 different climates with the 3 different types of technologies, but as we know, there are many different climates, there are many different geographies, and they're all going to be different. The same type of system that you would look to provide in climate zone 2B may not be the same type of technology you'd want to provide in climate zone 6A. However, we as engineers want to look at all the technologies available and all the nuances of that application. And the thing I want to try to impress to you today is that as we are looking at industrial facilities, some of the same types of decisions or design practices that we use either in commercial spaces or in different climates may not be the same. And what these technologies can do when we look at industrial facilities that are operating at different points on the psychometric chart than the typical vapor compression systems or the typical commercial spaces that we see today. So one thing I'll ask you to do is, as you look at your buildings and as you look at your environments and think about where you are in the market, think about what types of projects that you have come across. And when I'm looking at industrial facilities, what would an extra 12 degree, 15 degree, or even 25 degree type of temperature depression do for industrial space that has been consistently trying to provide cooling or more cooling effect in spaces that has not been able to achieve before? So I'm going to show up a big chart. There's a lot of numbers up here for you. I'm not asking for you all to download it all, but think about where you are. What's your typical climate zone based on that last map, and what would my representative city be? And think about if I was looking at an industrial facility, and I'm trying to think that today I might be only able to deliver a 91 degree of ventilation air that will provide some net cooling effect. But with the 3 different types of evaporative technologies, I might be able to provide enough of a cooling effect, enough temperature depression to get ourselves into that more safe conditions and try to get some of these facilities that are struggling with employee retention, safety, heat stress, and get a environment for these facilities that have had difficulties doing it in the past. So again, this is the current hurdle for all the industrial facilities. We have seen this happen before. When we connect with other manufacturers like ourselves, we are seeing many facility leaders trying to solve this problem. They have looked at it in the past, and every time they had looked at trying to solve it, the economics of it did not make sense. However, the industry has changed, technology has changed, worker conditions, a greater focus on safety has changed, and some of these equations don't look the same as they did before. However, one of the things that is constant that we see in our facility and we see at other industrial facilities is that there is one current hurdle that many industrial facilities have that has been pretty consistent across the board and across geographies. And it's, what am I doing with my ventilation load, right? So if you have a client that's in the manufacturing heavy industrial space and they start to even go down this exercise of looking at providing some level of space conditioning, the first thing we do as engineers, we say, what are you doing with your ventilation load? What about all this process exhaust? What are you doing? Why do you have that process exhaust? How much is it? And what are we going to do to counteract the now sizable portion of my overall process load, my overall space conditioning load, by counteracting that ventilation load? So the first step that we see a lot of facility owners do is they say, I have to start my ventilation with an indirect, a direct, or other types of evaporative technologies. This may actually give me enough where I can provide a level of comfort and conditioning to the space that I can, in effect, do everything I need to with one technology. Or if it's a facility that says, you know, I'm trying to provide even more temperature depression, I'm actually trying to provide space conditioning in my facility with dew point depression, with maybe some humidity control. But as we get into maybe an application where they do need some type of vapor compression, where they do need mechanical cooling systems, and now we're looking at chillers, large condensing units, and other types of systems, the first thing they're always going to have to approach is, well, how am I going to temper that ventilation load? And I know as a facility leader here in our facility, that's the first thing we had to do to counteract is how to be able to temper that ventilation air coming in. And if I want to go beyond that, what type of systems am I going to need after the fact? So this is a great technology that may get you all the way there, depending on your application, or at least it may make that next phase of cooling, that next phase of adding mechanical cooling, maybe a little bit more of a viable solution with making the ventilation load an easier, lower cost to install or lower cost to operate. And when we look at that ventilation load, and as we say, I'm getting to the point where I actually do want to provide some vapor compression, I do want to provide some mechanical cooling, I could do that either through mechanical cooling my ventilation load, or I can look at it from an evaporative cooling standpoint. And if we look at the operating costs, and this is really where evaporative cooling has shined in the past, is that the actual operating costs of trying to run a very simple system, very low pumping energy versus the higher connected kW of vapor compression, we have tremendous savings from an operating cost standpoint compared to traditional vapor compression or mechanical cooling systems. So when I'm looking at trying to temper my ventilation load, if I was using evaporative technologies or traditional mechanical cooling, there is a tremendous operating cost savings. So if we are looking at a facility that does want to provide mechanical cooling, there could be some combination of both indirect, direct, or two-stage evaporative cooling with other types of vapor compression systems to provide the total solution. However, my evaporative technologies is going to make the total operating cost of the system much less than if they were using it without that technology. And what are all facilities trying to do? They're ultimately trying to lower their risk. They're trying to lower their risk of safety instances. They're trying to lower their risk of quality. As we see in many facilities, we see in our facility, we see in other manufacturer facilities, as temperature goes up, as the conditions inside my space goes up, my quality issues may go up. So we're trying to lower that risk and make the overall systems for those employees better. I'm trying to lower my risk for employee retention, and I'm trying to lower my risk for employee recruiting as well. And again, the thing I think that we are seeing these facility leaders say is, I cannot afford to completely ignore the elements of heat stress on my safety anymore. More often than not, sometimes we were seeing these clients looking at providing cooling as some level of employee retention. However, the safety has become a extremely common item inside facility leaders that are trying to alleviate. They have ignored it in the past. However, with the addition of new technologies, with the changing workforce, with the changing working environments, many facility leaders are saying we can't ignore it anymore. So as you're talking with your industrial clients, the one thing we need to ask them again is, why are you changing? Why are you looking at these new technologies? Why is adding cooling or why is adding space conditioning to the space different today than it was before? What are the things that you are seeing inside your facility? What are you seeing inside your applications? What are you seeing inside of your workforce? The new technologies available today may actually be able to change that scope and change those questions that were answered differently before. We also need to understand and unpack what kinds of costs is my customer looking at trying to capture. Are we looking at just operating cost standpoints? Are we looking at the additional operating cost standpoints? Are we looking at the additional complexity of maintaining or of installing these systems? And ultimately what we're trying to do is look at the total cost of ownership. Look at what is it costing our industrial clients in a training purposes? What is it costing them to retain and attract new people? What is it costing them to train, attract, and keep those people in place? Or if we don't, how much is it costing them to retrain and retrain? Some of these large facilities without a proper safe working environment, there is a tremendous cost to retraining employees, sometimes 2, 3, 4 times throughout the year. So these costs all need to be encountered and accounted for when we're deploying cooling technologies in the industrial space. So ultimately, what I want you to walk away today is know that the evaporative cooling technologies is a viable solution and a viable alternative to other mechanical cooling systems. It allows us to provide a better temperature depression than general ventilation, and it may actually provide enough of additional worker comfort and temperature depression in these industrial spaces that have not been able to make it an economically viable project before. And think about how can these evaporative technologies help industrial clients in the large warehouse, distribution, or manufacturing spaces lower workforce risk and improve working conditions. How can that better conditions improve my productivity and ultimately make the spaces for hardworking people better? And additionally, as we talk about energy, as many clients are conscious of in the industrial spaces, is when we're looking at evaporative cooling technologies versus traditional mechanical cooling systems, what are the actual operating cost differences, and how can this new technology maybe make that a viable solution? So that concludes the end of all of the technical content, and it looks like we have some questions coming in, and I will turn it over here to Randy, and we'll answer some of your questions.
Thanks, Dave. I really appreciate the presentation. So we can get started here today. There's been a lot of questions. Several people have asked about water quality, some stating that water quality in their area is they have hard water. Some have stated, we know that water quality varies throughout the United States, and since it's a major component of evaporative solutions, is that important? And if so, how do we handle that as a company?
Yeah, thanks, Randy. That is a great question, and it is a application that changes tremendously. Sometimes, from state to state, from zip code to zip code, and sometimes even from address within the same area. So, I think the one thing that you'll see is always try to involve your local water quality experts, because they'll have a very good understanding of what are some of the challenges that you may be faced with at a very specific site inside even your backyard. However, when we talk about water quality, what we're talking about are what are some of the dissolved solids or salts or anything else that might be in my water. And I think the thing that I'd say is that there's a variety of things that you can do to address hard water or other types of water quality issues. In some cases, a simple dilution or draining of our systems over time will help stop any sort of mineral buildup or any other types of biology buildup, microbiology grow up as you have the water in your system. We have seen in some cases where a low level or concentration of some chemicals can help inhibit the growth of that. One thing I'll say on the indirect evaporative media that is unique compared to the direct evaporative media is that as scale builds up, maybe on those polymer plates, the heat exchanger is designed to have a little bit of a flex in it, so it will have its ability to actually shake some of that scale off, so that without introducing any sort of chemical, you can actually shake some of that scale into the sump, which will eventually get drained out through your bleed or your draining cycles. Or we've seen some clients use some actual measurements of total dissolved solids, TDS monitors, and using an actual feedback loop to vary the amounts of either bleed, of makeup, or of chemical in that system to help counteract any sort of buildup or solids in the water. Good question.
Here's another couple questions actually that kind of deal with water as well. It's about Legionella.
Yeah, that's a great question, a great comment. I think there's been a lot of energy and resources steered towards Legionella, specifically in ASHRAE itself. A lot of research being done and a lot of really neat solutions that are being developed. I think that's a good thing to look at. I think there are some things that you have seen people use inside of the evaporative cooling on cooling towers that would be consistent and translate over into some of these technologies, right? That's where we've seen some of the chemical, UV applications, or just in general ways of designing the systems and applying the systems to avoid that sort of stagnant water and stagnant air, moist air. Really the thing is we want to get that vapor out of the system and that warm vapor discharged and exhausted outside of the space and not re-entered in the system. So that's a good question, and I think that I would say look to ASHRAE and look to some of the other Legionella. They have a great Legionella guide, and I think even some new standards to help the counteraction and growth of Legionella, Legionnaire's disease.
A couple more questions about water. We've had a couple people say, what about recycled water, maybe from a golf course pond? Here's one about water from the rooftop drainage. Could those be used within an evaporative solution? And if so, or if not, what are some ramifications?
Yeah, I think that's a good question. I think there's most common applications, I believe, would be using city water or domestic water. You do want to have some level of clean water introduced into your systems, especially for the direct evaporative, right? We have maybe tighter flutes, and if there is any sort of solids or other types of things introduced in the system, depending on where your water source is coming from, is you may end up clogging those media and really reducing the effectiveness of that technology and maybe even actually destroying the media itself. I would say pond water, might have to look at it. It would depend on the type of water. I would say most common applications are not using pond water or other types of water and are using domestic. However, I think it's a great application, a great comment. If you do happen to have other types of cooling applications or DX system cooling coils that are evaporating water out of, say, a cooling coil, instead of draining that into the drain, and you have maybe a specific application that is not being currently cooled, that's a great spot to reuse that water and to not drain it and use that as your first stage of makeup into the evaporative technology. It's a great idea.
Yeah, here's the question somebody has about the Climate Zone 3A, and they were just wondering if a dehumidifier, dehumidification device could be added to lower the high wet bulb temperature. And if so, what would be the energy penalties that might be associated with it?
Yeah, I think it's a good time to talk about, these technologies can be used in tandem with any other type of device, right? So you actually could look at deploying a direct evaporative cooling technology with a traditional DX system. You could look at actually tying in a two-stage system with an additional chill water coil. So you can combine the various types of technologies, whether that's other type of mechanical cooling or whether that's other types of dehumidifiers. It all depends on what your application is. If it's an application that maybe I can get enough of what I'm trying to achieve without the addition of dehumidifiers or mechanical cooling, then that's where the evaporative cooling technology can shine. If you have an application that does need a little bit more depression, and we see this actually a lot in some ventilation systems, is they'll use the indirect evaporative media as your first stage of cooling, and then they'll use another type of mechanical cooling system, a DX coil, chilled water coil, to get me to where I really need to be to achieve what I'm trying to inside that space. But the indirect evaporative media greatly reduces the size of the chillers or the size of my mechanical cooling systems that I would have needed if I had not used this as my, in effect, pre-cooling or first stage of tempering.
Thanks, Dave. Here's one I'm going to throw at you. Somebody asked, is there an approximate cost per CFM?
Yeah, that's a good question. It definitely varies on your application, right? So these technologies can be as simple as a direct evaporative cooling only, or they can get as complex as a semi-custom indirect two-stage with energy recovery, stainless steel construction, and a variety of control technologies. So it's a pretty wide span, so it would be difficult to answer that directly. I think what you'll see is that these are primarily going to be larger CFM applications, but I've seen these anywhere from the dollar CFM to maybe 3 or 4, depending on how complex your construction gets based on the specific application.
Here's one. Is there a building size limitation where a building would be too small to use evaporative and or too big?
Yeah, I think that's a good question. It depends. I would probably say depends on your climate and depends on what you're trying to accomplish. More often than not, what we see these technologies being deployed at, these are not the type of direct evaporative media that you may see on some residential systems out in the Southwest climate, or even on some small workshops or automotive repair facilities out Southwest. We are usually seeing these in the 10,000 to 100,000 CFM range. So with that case, at least from the facilities that we are looking at and the projects that we've been approached, they are on the higher end, the 50,000 square feet and above, manufacturing to even warehouse and distribution centers that are $1 million plus. So I would definitely say looking at the larger facilities is more common, but not saying that it's only available or that it's not allowed to be deployed in smaller spaces. Just depends on your application, what you're trying to accomplish, and what kind of conditions you can achieve based on your geography.
Here's one. Somebody asked, are there concerns with high humidity in the space when utilizing evaporative cooling in a humid climate such as the Southeast United States?
Yeah, I think it's a good question, and it comes up a lot whenever we are looking at the technologies. I think if you looked at the high humid and high temperature loads of the Southeast, it depends on what your condition is. If I'm looking at a facility, an industrial facility that is extremely hot in the space, we have seen some direct evaporative technology deployed. Not many, but we've seen them deployed there. Again, it depends on where your conditions are in the space today. And if I combine my leaving air conditions with your room conditions, how is my mixed air going to be, and how is that going to? What is the resulting temperature going to be in the space? I would tell you that it's not in a clear saying you can't use direct evaporative in that Southeast. What I have seen some technologies or some facilities do fairly common, as we are looking in some of these facilities that need maybe a little bit of the benefits of the two-stage, my indirect and my direct, to help maybe calm any concerns of that added moisture or added humidity. We can add some simple controls, some some humidity measurements, and we can stage my direct evaporative media on or off based on whatever type of humidity conditions we are trying to maintain in the space. So I think what you'll see is that even in the Southeast, yes, there may be some conditions where I don't want to add any humidity, but those temperature hours may be fairly low. There actually will probably be a large number of temperature hours as we get off-peak design where I can get enough cooling and actually provide more of an effect by using both the indirect and the direct in those off-peak hours. And we may want to add a little bit of additional complexity controls to help turn and cycle that added moisture if they are concerned about humidity in the space. So hope that answered your question. Would love to look at a project and maybe go in more detail with that person, but feel free to reach out and we can talk about it offline.
So we're almost out of time, so I'm going to throw a really easy one at you here at the very end. A couple people have asked for your email address.
Yeah, would be happy to. I think you will have my contact information at the end of this presentation. You will get a certificate for joining this presentation. And if not, my email address is D as in David, BINZ @cambridge-eng.com. Would love to reach out to you and be able to continue the conversation if you have more questions, or even look at how can we get deeper into technology and how can we provide more cooling and more space conditioning in these spaces which have not seen in the past.
Thanks, Dave.
So with that, I think that concludes our presentation. Again, thank you all for your time. Hopefully you learned a little bit about evaporative cooling and how it can help industrial clients. And again, thank you all. Take care and have a great day.